Okay, so in this video, we're going to talk about how to predict the products when you only know what the reactants are. This is obviously a really useful thing to be able to do because you want to know, as a chemist, you want to know what happens when you put things together before you do it. It would be really nice to know when I put some zinc into my copper nitrate, what exactly it is that I expect to get out of this reaction. Chemists don't just go around throwing things together willy-nilly, hoping for the best in their products, and they have to figure out what those products are. They put things together on purpose to get very specific products, and I don't want to have to look up every reaction. Since I know some types and typically what's going to happen, I know that if I put one metal all by itself with an ionic compound with a different metal, that this metal is going to come in and displace this, and this one is going to come back out right here. For a single displacement reaction, this is the process that's happening. Now we just need to pay attention to what we're getting over here. Well, the zinc is going to go into the compound and the copper is going to come out. So I'm now going to have copper sitting out all by itself plus zinc nitrate. Now what I do need to pay attention to still is some of these formulas. Copper is very simple. Copper is a metal. Okay, it's just a monatomic substance. We simply write the symbol. But our zinc nitrate, we do need to pay attention to. We know that zinc is a Zn2+, and nitrate is an NO3-. So like we saw in our precipitate lab, this 2 right here has to do with the copper and didn't necessarily get carried along with it when the zinc came in. Now it happens to here because I still have a 2 in the zinc, and it's going to end up out there. So I am going to have ZnNO3, 2, like that. Now I'm going to need phase labels. Copper's a metal, right? That's what happens in these single displacement reactions, is I end up with a new metal hanging out here. Okay, and then we're just going to assume that this compound is aqueous. There was plenty of water available because I had this as an aqueous solution, so my zinc nitrate is probably going to be aqueous as well. Okay, and then we could balance that, but if you go through and check, you'll find this one balances all on its own. Let's do one last thing. Let's check now, just to make sure this is all well and good that I can write this, but does it actually happen? We learned in the last video, in the last lesson, that not all reactions actually occur. So we need to come over here and remember, single displacement reaction involves this list right here, this reactivity. And we're watching to see, is the zinc more reactive than the copper? Is the zinc able to kick the copper out of its place in the compound? So the zinc is right here, and my copper is way down here, right? Zinc is more reactive than the copper. And so yes, this is indeed spontaneous. Okay, so let's do another one. What if I had aluminum and some potassium chloride? Again, I find the arrows infinitely helpful. Okay, in a single displacement reaction, that's what happens. So I'm going to have now potassium plus aluminum chloride. I'm going to abbreviate. Okay. Potassium, again, as a metal, simply a K, plus aluminum chloride. Well, aluminum is a 3+ ion, and chloride is a Cl-. Okay. Remember, we need to switch those charges, so I end up with an Al with no subscript, Cl, and that's going to have a 3. Okay. Again, phase labels, your metal is going to be a solid. Your ionic compound over here is probably going to be aqueous. We could check the table that I'll talk about in a minute in the next video, but we don't care that much. We're just going to assume. Now, does it actually happen? Well, here's my aluminum here, okay, and my potassium way up there, which means that my aluminum is indeed not stronger than the potassium is, so this is non-spontaneous. Okay. We can balance it anyway. You'll get better at doing these in your head. Already we can see that the only subscript we've got is the 3 on this chlorine, right? So we're probably going to need a 3 right there to make there be 3 chlorine atoms, and so you'll need a 3. right here in your potassium to make this balance. Okay, so this is how we do single displacement reactions. Combustion reactions are by far the easiest ones of the whole set. Hold still. I touched the pages. Okay. Combustion reactions. Now, first off, you'll have to identify it, right? I'll just give you the things that are going in together, and you'll have to identify this reaction as combustion reaction. If there's the O2, it's probably a combustion reaction. Okay, we have a carbon and hydrogen compound reacting with some oxygen gas. This is going to be combustion. Well, you'll remember that our definition of a combustion reaction literally stated that it is a carbon and hydrogen and maybe oxygen compound that burns in air, okay, to produce carbon dioxide and water. And that water is going to be a vapor, so it's a gas. Okay, and carbon dioxide, also a gas. That is all there is to predicting the products of a combustion reaction. Once you've identified it, once you know that this is going to be a combustion reaction, the products are always carbon dioxide and water. And the water's a gas because, right, we burnt, when you set things on fire, they don't like drip liquid water, right? It gives off steam. Okay, if you hold your hand over a candle, you can feel the water, like, right, your hand gets wet. That's the steam from this combustion reaction. Okay, and again, we can balance. We'll do this the long way. See, H. No, this isn't hard, but just so you can see. There's 1 carbon, 4 hydrogen, 2 oxygen. I have 1 carbon here, 2 hydrogen, 3 oxygen. Okay. I'll need 2 water molecules. That makes this a 4. Changes my oxygen to 2 here, plus 2 there, gives me 4. So I'll need a 2 right here. 4 total. Is it spontaneous? Yes. Something made out of carbon and hydrogen is going to burn every time. Okay, so combustion reactions are always spontaneous. Okay. There you go. Okay.